In this problem and the next, we're going to talk about how to measure surface area and volume. So the goals of the day, GTD, woo woo, are to 1, introduce surface area and volume. Then we're going to explore problem 4.1, making rectangular boxes. There's a Khan Academy tutorial that you're going to view. Then we're going to have some additional practice homework, and then of course have fun. In this investigation, we are learning how to measure surface area and volume. Specifically in problem 4.1, we're looking at the surface area of rectangular prisms. But before we do that, I first want to talk to you about nets. And we have a video that describes it as well. But when you look at your textbook on page 78, you go to the second paragraph and it says, packaging engineers draw patterns or nets that can be folded to form packages. A net is a two-dimensional pattern that can be folded to form a three-dimensional figure. These patterns help determine the amount of material needed to construct packages. So we're going to watch a video on that.
Boxes come in all shapes and sizes. Shoe boxes, juice boxes, cereal boxes. They're everywhere. But have you ever stopped to think about how boxes are designed? Well, it can be very interesting and surprisingly complex. Package designers can't just draw a diagram and voila, a box is born. There are many factors they must first consider when making even the simplest of boxes. They must think about type of material, cost, post-use recycling, shipping and distribution, and design appeal. Then engineers begin drawing patterns or nets that can be folded to form packages. A net is a two-dimensional pattern that can be folded to form a three-dimensional figure. These nets help determine the amount of material needed to construct the packages. How these two-dimensional nets are used to create three-dimensional objects is an important first step in understanding packaging design. Without nets to help guide you, you could wind up with a box like this. What else might a packaging engineer consider when designing a package?
So looking back on page 78, the three-dimensional shape, it's called a unit cube because all of its edges are 1 unit long. But that cube is also an example of a rectangular prism. So how many faces does that cube have? Count them. Right? There's 1, 2, 3, 4, 5, and 6. So a prism is a three-dimensional shape with two parallel and two congruent or two of the same faces called bases. The other faces are called lateral or side faces and are parallelograms. So a rectangular prism has bases that are rectangles. The length and width of the rectangular prism are the length and width of its rectangular base, and the height is the distance from the bottom of the prism to its top. The length, width, and height of a rectangular prism are its dimensions. So look on page 79 and you see an example of a rectangular prism. Think about a shoe box that you might have at home. Think about a Kleenex box that you might have at home. It's got a length, it's got a width, and it's got a height. But when you undo that box, it's going to look similar to the net that you saw in the video. We are now going to look at the surface area of a rectangular prism, and to do that, I want you to watch this Khan Academy video.
Figure has a surface area of 40 square centimeters. The net below has 5 centimeter and 2 centimeter edges. Could the net below represent the figure? So let's just make sure we understand what this here represents. So it tells us that it has 5 centimeter edges. So this is one of the 5 centimeter edges right over here. And we know that it has several other 5 centimeter edges because any edge that has this double hash mark right over here is also going to be 5 centimeters. So this edge is also 5 centimeters. This is also 5 centimeters. This is also 5 centimeters. And then these two over here are also 5 centimeters. So that's 5 centimeters and that's 5 centimeters. And then we have several 2 centimeter edges. So this one is 2 centimeters, and any other edge that has the same number of hash marks, in this case 1, is also going to be 2 centimeters. So all of these other edges, pretty much all the rest of the edges, are going to be 2 centimeters. Now they don't ask us to do this in the problem, but it's always fun to start with a net like this and try to visualize the polyhedron that it actually represents. And it looks pretty clear this is going to be a rectangular prism, but let's actually draw it. So if we were to, we're going to fold this in, we're going to fold this that way. This will be, you could view this as our base right over here. We're going to fold this in, we're going to fold that up, and then this is going to be our top. This is the top right over here. This polyhedron is going to look something like this. So you're going to have your base. You're going to have your base that has a length of 5 centimeters. So this is our base. Let me do that in a new color. So this is our base right over here. I'll do it in the same color. So that's our base. This dimension right over here, I could put the double hash marks if I want, 5 centimeters, and that's of course the same as that dimension up there. Now when we fold up this side, let me do this in orange actually. When we fold up that side, that could be this side right over here. This side right over here along this 2 centimeter edge. So that's that side right over here. When you fold this side in, right over here, that could be that. That's that side right over there. And then when, of course, we fold this side in, that's the same color. Let me do a different color. When we fold this side in, that's the side that's kind of facing us a little bit. So that's that right over there. That's that right over there. Color that in a little bit better. And then we can fold this side in, and that would be that side. And then, of course, we have the top that's connected right over here. So the top would go, this would be the top. And then the top would, of course, go on top of our rectangular prism. So that's the figure that we're talking about. It's 5 centimeters in this dimension. It is 2 centimeters tall, and it is 2 centimeters wide. But let's go back to the original question. Is this thing's surface area 40 square centimeters? Well, the good thing about this net here is it's laid out all of the surfaces for us, and we just have to figure out the surface area of each of these sections and then add them together, the surface area of each of these surfaces. So what is the surface area of this one here? Well, it's going to be 5 centimeters times 2 centimeters, so it's going to be 10 square centimeters. Same thing for this one. It's going to be 5 by 2, 5 by 2. This one is 5 by 2. So these are each 10 square centimeters, and so is this one. This is 5 centimeters long, 2 centimeters wide. So once again, that's 10 square centimeters. Now these two sections right over here, they're 2 centimeters by 2 centimeters. So they're each going to be 4 square centimeters. So what's the total surface area? Well, 10 plus 10 plus 10 plus 10 is 40, plus 4 gets us to 48 square centimeters, or centimeters squared. So could the net below represent the figure that has a surface area of 40 square centimeters? No. This represents a figure that has a surface area of 48 square centimeters.
Now that you've had the chance to watch the 2 videos, I want you to do some practice that's also on Khan Academy. When you get there, it should look like this, but the link is included above, and it's also included in your Google Classroom.